All right, guys, chapter 3, big picture. What are all the things that we talked about in this chapter? The first thing we looked at is functions inside of functions. If you have a function inside a function, this is your red flag to use the chain rule, right? And so if I'm looking at this function, it's not just plain old e to the x, it's e to another function. So I'm going to apply that chain rule. And so that means I take the derivative of the outside function, keeping this is what we were calling u, right? So I have e to the u times the derivative of u, or u prime. So I'm going back and taking the derivative of that inside function. And you can do this as many times as you need to. If you have function inside a function inside a function, you apply the chain rule repeatedly. Next thing we looked at is if you have a function in terms of x and y. This is when we do implicit differentiation. Everything else we've seen, the function is just in terms of x. But if you see x and y in the equation, that's your red flag to do implicit differentiation. So in this example here, we have x and y. We have another y here in the equation. So when you do implicit differentiation, you proceed like normal. So here I've got a first and a second. I'm going to do a product rule. So I have first times the derivative of the second. Anytime you take the derivative of y, that's when you have to implicitly do your chain rule here, dy dx. If this variable doesn't match this variable, that's when you have to include this term. Anytime you're taking a derivative and this bottom variable here, what you're differentiating with respect to, if it's not the same variable, then you have to include this dy dx. Where was I? So I had the first times the derivative of the second plus the second times the derivative of the first. And you'll notice here that since I wasn't taking the derivative of y, I don't have to include that dy dx term. It's only when you're taking the derivative that you include that term. And then I'll go take the derivative on the other side here. Derivative of natural log is 1 over y. Since I'm taking the derivative, and this is a y and not an x, I add on dy dx. And then from there, you know what you do. You gather your dy dx terms on one side of the equation, move anything that's not dy dx to the other side, and then factor out a dy dx, divide by everything else. So you can get dy dx by itself. And then kind of randomly after that, we had this thing called L'Hopital's rule, and it's just kind of stuck there in the middle of this chapter. Couldn't teach it to you during limits because you didn't know how to do derivatives yet, but you know now, right? You can only apply L'Hopital's rule when you end up with a limit that is indeterminate. So remember, the first thing that you always try on limits is you try direct substitution. Take this number and plug it in everywhere that there's an x. So here I'm going to end up with 2 squared plus 2 is 6, minus 6 is 0. And then 2 squared minus 4 is 0. And so remember, that's our, oh no, that's indeterminate form. If you have 0 over 0, or if you have infinity over infinity, those both count as indeterminate. Only when it's indeterminate, you can apply L'Hopital's rule. And what L'Hopital's rule says that you can do is you can take the derivative of the top and take the derivative of the bottom, okay? And you're going to notice you'll have mixed review tests, for all your chapter tests. Now that you know how to do this, you can use the shortcut. Back when we did chapter 1, the only way that we could attack this problem was by factoring it. Well, taking derivatives is a lot faster than factoring. So if I go to take that derivative, if I rewrite that problem, I've got the limit as x approaches 2 of 2x plus 1 over 2x, and then I try direct substitution again, and then this time I get 5 over 4, and that is my limit. If you try direct substitution again and you end up with 0 over 0 again, you can apply L'Hopital's rule twice. You can take the derivative of the top and the derivative of the bottom again. Okay, so yeah, this was a random topic thrown in here, but you can use it now for the rest of the year. It's a great trick to have up your sleeve. You've got it. Next thing we can do is higher order derivatives, and these are real easy. You start by taking the first derivative. If it asks you for the second derivative, you just take the derivative again. there's that f triple prime of x. You may also see that written as f3 of x. And this number can be anything you want. You can take the fourth derivative, you can take the 100th derivative if you want to. That's really the only thing to remember on this section, is just look out for the different notations. You might see one that looks like this. That's telling you to take the second derivative. That y may or may not be there, still telling you to take the second derivative. You might see y to the 15th. That's telling you to take the 15th derivative. So just be aware that you can see the primes, you can see the numbers like this, or you may still see the dx terms. Next thing we looked at was particle motion. And here's the big picture. What I need you to remember is you have the position. You can take the derivative of that to get the velocity. You can take the derivative of that to get the acceleration. This sequence here, I really need you to know, right? You have position, take the derivative, get the velocity. You have the velocity, take the derivative, and you have the equation for acceleration. The other things I really need you to know is if the sign of velocity matches the sign for acceleration, so if they're both positive or if they're both negative, that tells you, drop my stylus, that tells you that the object is speeding up. And all the positive and negative really means that's just our conventions for to the left or to the right of the origin, right? So if they're both positive, it's speeding up to the right. If they're both negative, it's speeding up to the left. If the signs don't match, if the sign for velocity does not equal the sign for acceleration, one's positive, one's negative, doesn't matter which is which, that tells you that the object is slowing down. The other real common question with these particle motion problems is where is the object changing direction? And here's what you have to know. If the velocity is equal to 0, if the velocity is equal to 0 and the acceleration is not equal to 0, then we know that the object is changing directions. Object change directions. Both of those things have to be true, right? If v of t and a of t are 0, if they're both 0, all we can say is that the object stopped. We have nothing to tell us that the object changed direction. We only know that the object stopped. It could keep going in the same direction. Could have been going, stops, and then keeps going, right? The only way that we can say the object changes direction is if it's going, it stops, and then it goes back in the opposite direction. We can only say that if the velocity comes to 0 and the acceleration is not 0. And then last set of problems, these were my favorites, the related rates. These are the word problems. These are always word problems. And we have a good routine. They're the hardest, but we have a good routine for them. Your first step is always to choose a geometric formula. Always choose a geometric formula that matches whatever shape is happening in this problem. And then your second step is always to differentiate with respect to time. Okay? So for example, let's say I'm talking about the area of a triangle. Let's say that's the geometric formula that I choose. The first thing I need is that area formula. And then the next step is always going to be to take that and differentiate it with respect to time. Now remember what we talked about with implicit differentiation. Because this t doesn't match any of these variables, anytime I take a derivative, I have to tack on something dt to the end of that differentiation. So if I differentiate a, the derivative of a is just 1, but because a doesn't match t, I say dA dt. And then here I have a product rule. I've got a first and a second. So I've got the first times the derivative of the second. Well, it's just 1, but because t doesn't match h, I have to say dH dt. Plus the second times the derivative of the first. Because t doesn't match b, I have to tack on dB dt, following that chain rule there. And then what you look for is you hunt through the problem and you're looking for numbers that you can plug in here. Any of these dt terms are going to have a unit that says something per time. So you're looking for things like centimeters per second, miles per hour. It's always going to be something per time, those are the kind of numbers that go into your rates here. These dH, dt, dA, dt, those are all rates. And then these will be the constants at that point in time. Now, if you have a variable that doesn't change at all, let's say you had, a equals 1/2 BH, but you're told that the base of the triangle doesn't change. The base of the triangle is constant. That word constant means that you can treat it like a number. I can lump these together as a number if it's constant. So then when I go to take the derivative with respect to time, I still have dA dt. But then this constant gets pulled out front, and I just have to worry about the actual variables. Right? And so there I have the dH dt term. So if it tells you that a variable is constant throughout the entire problem, you don't have to differentiate it with respect to time. Just lump it in with your other constants. It gets pulled out front whenever you're taking the derivative. I think that hits all the highlights. This was a busy chapter. We did a lot of good things here.